Okay, so let's try to solve our office assignment puzzles. Maybe not as exciting as chocolate, but kind of very real life application. So for that, in order to talk about it, let's introduce a term, permutation. So you permute things when you change the order of them. So if you have a list of people, for example, me, Dave, Oscar, and you, Andrew, and you permute this list, you could get, for example, Oscar, Dave, you, Andrew, and me. So how many ways are there to permute a list of n people? This is exactly the question of how many ways there are to get 4 offices to us, because maybe if you list them as Oscar, Dave, you, Andrew, and me, then Oscar gets the first office, Dave gets the second, you, Andrew, get the third one, and I get the last one. So here's how you can count how many ways you could do it. There are 4 people who can get the first office. 4 choices. Okay, now that the first person one person got assigned to the first office, this leaves 3 choices to pick for the remaining 3 people. When one of us gets that office, the second office, there are 2 choices left for the remaining people, and for the last person there is no choice. So by the product rule, we get 4 times 3 times 2 times 1, 4 factorial different ways of assigning 4 people to 4 offices. And that's exactly the number of ways to list our names in different orders. Like me, Dave, Oscar, you, Andrew. Me, Dave, you, Andrew, and Oscar. And so on and so forth. Try it yourself. So in general, if you have n people, then the number of permutations, or just n element, then the number of permutations of them is n factorial. So basically, if you have n things, there are n factorial ways to list them in order. Now we could generalize to talk about not just 4 people, but add to that part about selecting 24 people, selecting 4 people out 24 to go to Earth Sciences, and then assigning offices to those 4. So how can we do it? Again, we could use the rule of product. So now, rather than picking 1 out of 4 to go to ER 6030, we pick 1 person out of 24 to be in that office. That leaves 3 offices and 23 people. So the second office, we get 24 possible people assigned to it. The third office, we get 22 people. And the last office in Earth Science, the fourth, we get 21. And this gives us a formula for calculating how many ways to assign offices to not all of people in our list, but only a certain number of them. So here is another way to calculate it. So there are 24 offices in engineering and earth science. So there are 24 factorial ways to assign offices to everybody. So how many ways are there to assign offices in the engineering? It's 20 factorial. And the number of ways to assign offices to some 4 people, to select 4 people out of 24 and assign them to offices in earth science, is number of all possible ways to assign offices to everybody divided by the number of ways to assign offices in engineering, because for this particular question, we really don't care who gets which office at the engineering building. We only care who gets which office at the earth science. So in general, here is the formula. The number of R permutations out of n objects. It's R because we are selecting R out of n people, and it's permutation because we care who gets which office, is n factorial divided by n minus r factorial. That is number of all possible permutations divided by number of permutations of people assigned to offices that we don't care about. So here is another example. So suppose you have a contest in which you have one first prize, one second prize, and one third prize. And you have n participants total. So there are n choices for the first place. Once you selected the winner, there are n minus 1 choices for whoever gets the second place. After you selected the second place, there are n minus 2 choices for the third place, and nobody else gets any places, so you really don't care about the full ranking. So putting this into the formula, we get the 3 permutation out of n objects is n factorial divided by n minus 3 factorial, which is n times n minus 1 times n minus 2. Okay, but now suppose we don't even care who gets which office. Suppose we just want to know how many ways to put 4 people into earth science and leave the other 20 at the engineering building. So how can we calculate that? There are 24 factorial ways to assign offices when we care who gets each office. 20 factorial ways to assign offices in engineering, 4 factorial ways to assign the offices in earth science. Well, and now our final answer is 24 factorial divided by 4 factorial. That is, we consider all the possible orders of assigning offices in earth science to the same 4 people as the same thing, and divided by 20 factorial, where again we consider all possible ways of assigning offices to people who are left in engineering. If they're the same 20 people, we consider them to be the same. So this is now called not a permutation but combination. In permutation, we really cared about order of things, what is the sequence of things. In combination, we just care about number of ways to choose k people to go to, for people to go to earth science, k objects out of n objects. And in fact, this notation is pronounced as n choose k, and c of nk is another way to write it, but chances are you're going to see this as n choose k. And this is exactly the formula that we just derived. N choose k is n factorial divided by k factorial divided by n minus k factorial. So n factorial is the numerator and k factorial times n minus k factorial denominator. So here is an example. So suppose you have 30 people training to be astronauts and you need 6 of them to go to Mars. How many ways to select 6 people out of 30? It's, well, a little under 600,000. And soon when we'll be talking about probabilities, we will be using this kind of calculation to say, so if you're on the team of 30, what is your chance to go to Mars? Okay, for the next time, let's look at slightly more complicated scenario with combinations. So far, we just talked about non-repeating things. We were selecting 4 people to go to earth science out of 24. Well, we cannot repeat people to go to earth science. But imagine that 10 of you came to the office hour and 11 of us decided to go and get some coffee. We come, say, to Jumping Bean, and they sell 6 types of coffee drinks. Here's the question: how many possible orders can we place for drinks? So there are 11 people, some get one kind of coffee, maybe some get another kind of coffee. Say each one of us get just one drink out of those 6 possibilities. So how many different combinations of drink can we get? And here, me getting cappuccino and somebody else getting espresso is the same as me getting espresso and somebody else getting cappuccino, because we are still going to order like one espresso, one cappuccino, and all that stuff. So say one combination is everybody getting drip coffee, another one is 6 get espresso and 5 Americano, and so on and so forth. So this is a little bit more involved than the combination permutations we did so far, but we will use some of the same ideas and talk about it in the next lecture.